Hello, this is Dr. Chad McGee again. Today we're going to be talking about photons, getting into more quantum physics. Okay, so most people associate photons with light energy. They're kind of interchangeable. And in my last discussion with you, I talked about how light actually is more of a spiral. So it's a three-dimensionality vector twisted around a cylinder such as like this, okay, so that it twists around and curves. Well, that leads into some kind of interesting things. So what actually is a photon? All right. As we know per many different rules, photons have duality, okay? So that leads into, well, what would be the geometry of a photon? Okay, well, based off of what I know, okay, so this is our rough representation of the light vector being twisted around a cylinder, okay? So this is the electrode. And remember, we have the magnetic portion that goes like such. Okay, so this is the magnetic. Well, my perspective on this is that photons are essentially light vectors that loop around itself. In other words, in this process where it's looped around the light vector, it's coiled, it bends upon itself and somehow gets mysteriously looped. So that's my definition of what the photons actually are. They're looped light coils. Now that gives them kind of some special properties because they have that looping effect. Now they don't have the full effect of what matter is, but it does give them some special properties of particles. So we think of interchangeably photons as a form of particles, but they're not fully matter. They're made out of light energy, but yet they're a little bit different. This would kind of give a reason why that they're that way. Now, the take-home message from this is, okay, so this is light energy. Okay, the electromagnetic spectrum. This part here is interchangeable. It's very easy for them to become coiled up, make the photon, and then uncoil themselves and we go back to light energy, traditional electromagnetic radiation, what we consider light. Okay, so this in a nutshell is what my take is on the geometry of a photon. Now, where this coil part is inside and how big it gets for the coil, that I have no clue on. I'm not even going to speculate. I'll try, but I'm not going to be very accurate. I mean, I could guess that it's at the end. It could be at the very beginning. Who knows? Okay? This is kind of one of those take-home messages that sometimes even the people that think they know might not even have a clue. And I'm going to just flat out tell you, don't have a clue on that one. This is my best guess for the geometry on it, is that we have something of that vector that becomes looped within itself, and that creates those what we call photon properties. Now, I do want to talk about electrons again. In fact, I want to talk about electrons that absorb photons. Okay.
Hey, how are you?
Yeah, good. Okay, so most Gen Chem classes are used to talking about the photo excitation, okay? So in other words, a photon gets absorbed by an electron and it gets promoted up into an excited state, okay? So this is very commonly seen in most Gen Chem courses, that where you have an electron in the ground state, it gets excited up to the excited state. Well, we do know that this photon has to be of a certain type of energy. That's a quanta. It has to make it to the whole step. That's part of the quantum effect. It has to reach up to a certain step. Why is it that way? Well, let's revisit what I classify as potential geometry of an electron. Okay. So in this particular case, remember that this is in kind of an important detail. For all practical purposes, I'm drawing matter in a clockwise direction, but in reality, it may not be. It may actually be counterclockwise. And in my other drawings, of course, the antimatter I'm drawing anti-clockwise. But the net effect really is not so much which directionality it is at that moment in time, it has to do with when it was created. When you look at how this directionality of the light is formed, it has a certain directionality of the spiral, okay? If it's easier for it to spiral into itself, that creates matter. And this is a simplistic form of an electron that coiled within itself, made matter. Now a positron, that coils against the coil, okay? So in other words, it's going against the grain of the coil and forming the other direction. Now that's harder to do, and so therefore that's why it's much harder to find the antimatter form out in the environment, okay? Now I want to show you here that as an electron, this is ground state electron, goes up and absorbs light energy and gets to an excited state, it actually gains a bit in mass, okay? So this part right here came from light energy absorbed. Okay? Here's your original electron, but there's the piece that actually got inserted in. When it absorbed that light, it actually grew in mass. That's a relativistic effect. Part of that is then it pushes itself away from the nucleus of the atom. Okay? Thus, the radius that it's orbiting around must increase. Okay? So that pushes it further away. Now, as for what happens when it gives off energy, of course, so if it falls down, okay, it's going to emit this HV out, okay, and it's going to go back to the original size. So basically, as they start off, ground state, that's the lowest allowed that it can do, it gains energy, it grows bigger, okay, gets up to an excited state, further away from the nucleus, okay. If it gains up so much mass and it gets way far away, of course we know that is a photoelectric effect. It will leave, okay. That's something that was well publicized 100 years ago, that basically the beginnings of how do you basically cause materials to emit the electrons in their excited states. There you go. Okay. Now, this gets into something kind of strange. One of the big things that's always kind of confused scientists is not that electrons flow around a nucleus, but why. In other words, the directionality, why do they travel the way they do? Right now, we give predictions. So in other words, it's very hard for us to actually guess exactly where it's going and where it's going to be momentum-wise. Okay, that's your Heisenberg uncertainty principle. Well, to put it bluntly, I think I might have possibly figured a way that you might be able to, quote-unquote, beat the Heisenberg uncertainty principle. And that has to do with why does this electron flow around the nucleus the way it does? Now, this leads into a discussion back in our previous one where we talked about protons. Now, this is a rough drawing of the proton. Remember, we have spin pairing of two sets of your light vectors, and then you have one additional left over. That's the directionality vector, and because of that, that's why it has a +1. This guy and this guy have an interaction. Well, this guy's going to spin. And as this guy's going to spin, of course it has this magnetic field that spins around too, this is going to force this guy to move also. So as this guy spins around, this electron is going to want to tumble too. Okay? So the main take-home message is the inside nucleus of your atom isn't just a static space. You've got protons and neutrons are constantly moving around, jumbling, jostling around, and that's influencing the electrons themselves. You can kind of think of like the inside of the atom as a bunch of bar magnets, okay? Then you've got a little tiny magnet over here that's feeling the effect of all these magnets jumbling around. It's going to force that guy to move different directions based off of where the different particles are at, okay? So that's why electron orbitals are not quite so easy to understand why the things move the way they do, okay? That's kind of my take-home message is, gosh, the things become complicated, right? Yes, they can. Now,